Obviously, carbon cycle cannot be complete without discussing coal, oil, natural gas, and so on, which is what we are burning. Sorry about this figure here. I think I expanded it too much. It's got lost the resolution a little bit there. Let me change that before I go back. Basically, we know that over Earth's history, as we saw before, carbon has been playing a role, still not the best, but you can see, I hope. How coal was formed. So 300 million years ago, we talked about pre-Cambrian, which was before 540 million years ago, and then the explosion of maybe 25 million new species and the post-Cambrian. And that evolution also involved vascular plants during the Silurian, Devonian, Ordovician, and so on. And so many plants evolved and started photosynthesizing that they drew down a lot of the carbon. And along the way, before the dinosaurs, many giant plants had died in swamps. So it depends on the hydrologic cycle, rain, where they had colonized land, how the continents were configured, and so on, which we will look at in a minute. And over time, by 100 million years ago, you had a sea level change. A lot of dirt got put on top of the dead plants. So for millions of years, the plants were buried under water and dirt. And heat and pressure turned the dead plants into coal. And there are details. For example, freshwater coal is purer. It's got no sulfur, but salt water burial of the organic matter ends up having sulfur because of the salinity in it. And that coal is dirty. When you burn it, you're going to get sulfate aerosols and acid rain and so on and so forth. So over time, rocks and dirt build up, and you have what we have now. So you have to go mining for coal, and there is obviously lots of coal. It's very dirty fuel, so we don't want to burn it. But if you continue to burn it, we could probably burn it for many centuries still at the rate we are consuming it. But oil and natural gas also got formed along the way. So if you go to 300 to 400 million years ago, tiny sea plants called phytoplankton. Plankton means drifter. They don't usually swim, and they photosynthesize. And then there are animals which eat those plants. So they all died and were buried on the ocean floor. And over time, they were covered by layers of sand and silt as well. So going from there, you can imagine the time. It takes tens to hundreds of millions of years over which the plant and animal remains get converted into under heat and pressure into oil and gas. The idea of looking at the structure of the sugar and the protein was that these processes tend to exude oxygen and other materials and leave the fatty, oily parts and give us oil and natural gas. And of course, there are differences in the way they are formed. So you have then over time sand, silt, and rock remaining as sea level changes, and today we drill down through the layers of sand, silt, and rock to reach the rock formations that contain these oil and gas deposits. So Middle East, for example, has almost all of the oil and about 50% of the natural gas, and Russia has about the rest of the natural gas. And natural gas is hard to transport. It's liquid, so it tends to leak out, so it has to be compressed or transported as liquid carefully in high pressure. So it's not as easy to transport as oil or coal, for example. Petroleum is essentially the same process. You can see the same time periods and same processes leading to oil and gas deposits. The difference is that petroleum is like crude oil, but it has additional petroleum products. But often petroleum products are also made from a barrel of crude oil. So here you can see residual oil, hydrocarbon gas, liquids, distillate, jet fuel, gasoline, and so on and so forth. So often petroleum and oil are used interchangeably. Okay, so what are the kind of feedbacks that make the carbon cycle moody? We said moods of carbon cycle. So before, in the last podcast, I said Vostok and then said Dome C, which is obviously wrong. Vostok is there, Dome A, Dome C, Law Dome, Taylor Dome, South Pole, Sipel Dome, and all are here. This time series we looked at, I will spend a little bit more time here. This is 400,000 year long. This is the depth of the ice core that is drilled, but now it's been extended, so this time series now goes back to almost 1,000,000 years. So what is shown here is the temperature. So you can see the temperature has this sawtooth pattern with an abrupt warming and slow cooling, abrupt warming, slow cooling, and so on. And during the cooling time, carbon is drawn down, goes from about 280 ppm down to about 200 or less. Then during the abrupt warming, it jumps back up to 280 to 300, and so it also has this sawtooth pattern. And methane follows pretty closely behind. And Milutin Milankovitch showed us before that, James Kroll, that insolation changes over various timescales that are related to the ellipticity of the Earth's orbit around the Sun, the obliquity or the angle it makes with the the orbital plane of the ecliptic, and the precession or the wobbling of the Earth itself, and the precession of the equinoxes, which I won't go into. You know, there are equinoxes where sun is on the equator, the equal day and night everywhere, and you have solstices. That itself keeps moving around because of the gravitational pull of other planets. Here it says insolation in joules at 65 north. This is a critical latitude because because of orbital changes, radiation energy at 65 north changes, that will change the amount of snow and ice that will melt in the northern hemisphere, where there is more land and easier to build snow and ice glaciers on land. So that allows it to either keep building or keep melting, depending on whether the radiation increases or decreases. Right? So the key thing we are going to look for is these feedbacks. So various proxies are used, like delta O18, to measure connections to orbital parameters and temperatures. Methane and CO2 are measured in the bubbles, and so on and so forth. Okay. So what are we looking at here? Why is there a slow cooling and slow reduction in CO2, fast warming and a fast jump in CO2 and methane? Essentially, when the insolation increases, for example here, at 65 north, the glacier begins to melt, and that reduces the reflectivity and the loss of solar radiation back to space. So reduces the loss of energy to space. More is retained and absorbed by, let's say, the ocean. That increases the Earth's temperature and further melts the glaciers, and this melting phase can go really, really fast. And when that happens, there are various processes like exposure of old buried organic carbon or exposure of the ocean surface and so on, where oxygen can be belched out back into, the carbon dioxide and methane can be put back into the system. So there is a corresponding increase in methane and carbon dioxide. We don't completely understand where this number, about 100 ppm change from glacial to interglacial, comes from, but the main thing is there is a positive feedback between the carbon cycle and the temperature. The temperature change is initiated by orbital forcing, and then carbon dioxide begins to increase, and that traps more energy and adds to the warming, so there is a positive feedback. And in this phase, as let's say insolation is reduced at 65 north, which begins to reduce the melting of snow and increases the glacier volume and extent, which increases reflectivity, loses more energy, so cools the temperature further, but the oxygen carbon dioxide begins to drop, which also reduces the greenhouse effect and cools the temperature further. So again, CO2 is a positive feedback here in the other direction. Why does this go slower? Obviously, as temperatures cool down, the ability of the atmosphere to hold moisture goes down, which means the snowfall rates begin to drop and the building of glacier becomes slower and slower and slower. So it goes on, but it goes on for order 100,000 years, whereas this is much faster. And we know that in the recent end of the last ice age, there were hiccups that happened within 10 years or less. So this is a very rapid phase. Both are positive feedbacks, but one is a very rapid feedback, one is a very slow feedback. And we see here that in the recent times we have been increasing CO2, so it's the increase in greenhouse gases, and of course we are increasing methane as well, that are causing the warming, and the temperature hasn't caught up yet. So you can see there is a rapid increase in CO2 and methane, but the temperature increase is not as fast. But we know that over time these are the rates of interactions or feedbacks between carbon dioxide, methane and temperature that are going to kick in. So even if we stop the emission of carbon dioxide here, the warming will continue, eventually reaching these kinds of feedbacks, which is referred to as committed warming, or the warming we have already committed to by the amount of greenhouse gases we have already put into the system. So we talked about the long-term negative feedback that we will come back to again of carbon cycle, where geologic timescales, we said if it gets warmer, weathering rates go up, CO2 is drawn down, and greenhouse gas effect is reduced, which will reduce the warming. Whereas if it cools down, then the weathering rate is reduced, CO2 drawdown is reduced, so greenhouse effect goes up, cooling goes down. So why is CO2 behaving in these two very different ways, where it is a slow negative feedback in one time scale, a geologic time scale? At the glacial interglacial time scale, it's a positive feedback. Okay, so the book talks about how it's like having a crazy thermostat which does different things at different time scales. But anyway, we will just call this the moods of the carbon cycle, where it can behave differently at different time scales in the Earth system. Okay.